over matter and measurement. These are the objectives you should know at the end of the video, and if not, you need to go back and review it. So let's get started. I want you to know the difference between a theory and a hypothesis. A hypothesis is a proposed explanation. It's going to be something that you can test. It's not an opinion. You have to be able to test a hypothesis. You have to be able to develop an experiment to test your hypothesis. A theory is a well-tested explanation. Again, it's tested. It's not the theory in English where it's just an idea. A scientific theory is very well tested, multiple hypotheses to prove your theory. Scientific notation, a way to express very large or very small numbers. There's two parts to scientific notation. The first is the coefficient. Oops, I spelled that wrong. That's a C. And the coefficient has to be greater than 1, but less than 10. And then you're going to multiply that by 10 raised to some power. So for example, if I have 3.6 times 10 to the 4th, all that means is I take 3.6 times 10 times 10 times 10 times 10. So I got 4 tens, which is 36,000. Or a short trick is this power tells me how many decimal places to move. So since this 4 is positive, I'm going to take my decimal point and move it 1, 2, 3, 4. And then just fill in these little bumps with zeros. And I can do the same thing for a negative power. So if I have 8.1 times 10 to the negative 3, that means I have 8.1 divided by 10, divided by 10, divided by 10, which gives me 0.081. And since this power is a negative, that means I'm going to take my decimal point and move it 1, 2, 3 places to the left and fill in with zeros. Alright, accuracy and precision. Accuracy is how close you get to the true value. This is usually one measurement. You're looking at one particular measurement and seeing how close you got to the accepted value. So here, if you look at the bullseye, all these darts represent a measurement, and the bullseye is the true value, and so these would all be accurate. Precision is about if you can reproduce your measurements. If you are going to measure 10 milliliters 8 times, how close are you going to get each time? So precision is looking at a set of measurements. So here again, you've got good accuracy, good precision. Whoever threw these darts, I know, is probably going to hit the bullseye again if they do it a 4th time. Here we've got terrible accuracy. They're really far from the true value, but if they were going to throw another dart, I know that dart's probably going to land over here. So they're precise but not accurate. This poor person has really bad accuracy, really bad precision. I don't know where the next dart would be thrown. And so this would be horrible in a lab. In a lab, of course, we want good accuracy and good precision. So we can calculate the percent error, how close you got to your true value, with this equation. Percent error is the absolute value of the accepted minus the measure over the accepted, and then multiply by 100. So let's go through an example problem. A student measured the volume of a big container. He found the volume to be 65.7 liters. However, the real value for the volume is 50.2 liters. What is his percent error? So my percent error, start with my equation, is my accepted, which is the real value, so 50.2, minus the measured, and he measured it to be 65.7, divided by the accepted value or the real value. So we get 15.5 over 50.2, which gives us 0.308, which is 30.8%. That is really high. We do not want a 30% error in the lab. Let's do another one. Why don't you try this one on your own and hit pause and then come back and see if you got it right. A student measured a flask of boiling water to be 97.8 degrees Celsius. Water actually boils at 100 degrees Celsius. What is the percent error? So my percent error is my accepted, which is 100, minus my measured, which was 97.8, and divide it by my accepted, which is 100, and then I will multiply that by 100, whatever I get here. Okay, so 100 minus 97.8 is 2.3, divided by 100 is 0.0023, and then times 100 to get rid of my decimal, and I get 2.3, which is not bad, percent. That's not bad. Alright, significant figures. Significant figures include all known measurements plus a last digit that is estimated, and this is how we're going to report our precision in the lab. Now you have your rules for your significant figures in your reference chart, so they're always in the back of your book, and you will have this chart on the EOC exam. So as long as you know how to interpret these rules, you'll be good. So let's look at them. So number 1 says non-zero digits and zeros between non-zero digits are always significant. So a non-zero digit is just what you think it is. 1, 2, 3, anything that's not a digit. Alright, so 1 through 9 is a digit, and then any zeros between non-zero digits are significant. So 101 has 3 significant figures. That 0 counts. 100001, all these zeros count. So this number would have 6 significant figures. I'm just going to abbreviate SF. Number 2, leading zeros are not significant. That means if I have a decimal point and I have all these zeros and then my number, this number still only has 1 significant figure. All these zeros do not count. Zeros to the right of all non-zero digits are only significant if a decimal point is shown. So if I have 23,000, only these 2 digits count as significant. These zeros are not significant. So this would have 2 significant figures. Now, if I add this decimal point, I have made all these zeros significant. That means I can report this number with precision and accuracy to 5 significant figures. For values written in scientific notation, the digits in the coefficient are significant. So whatever I write before the times 10 to the whatever is here is significant, whatever that may be. So this would have 2 significant figures. Number 5, we're going to save until we do pH math. We're not going to worry about that right now. Alright, some common algorithms. So when you start adding and subtracting numbers, you have to keep your significant figures. So let's say we've got 12.1 plus 8.03 plus, I don't know, 1200.267. Whatever my number comes out to here, I have to keep the fewest number of decimal places, which is this number right here. I've got 1 decimal place. So whatever my answer comes out to be here, I can only keep this decimal place. I can't go out to the hundreds or the thousands. I'm going to stay in the tenths place. With multiplication and division, I'm going to round my answer to the least number of significant digits. So if I have, let's say 9.67, this number has 3 significant digits. If I'm going to multiply that by 101.2, this has 4 significant digits. And then I decide I'm going to divide everything by 4.6. That has 2 significant digits. So whatever my answer is here, whatever it is, I have to round so that my final answer has 2 significant digits. Okay, you also have to report significant digits when you're measuring in the lab. It's like this beaker. If you look at the labels, 10, 20, 30. That means this beaker can report 2 significant digits plus a last estimated digit, 2 sig figs. There's no way you're going to get, if you're measuring with a beaker, 29.862. That's impossible with this measuring. So if I'm measuring out of this beaker, the best I could say was probably about 28. 2 significant figures. Now if I'm measuring with this graduated cylinder, I know for sure two digits here plus a last estimated digit. So I would say this is probably 28.3. So this is 3 significant figures. Again, I'm not going to say, oh, 28. Nope, I need 3 significant figures when I'm measuring with a graduated cylinder. And then you get even more precise with a graduated pipette. So I know 28.123. I know this for sure because of these markings. So I know 28.3 for sure. And then my last estimated digit, maybe like 3.2. So this has 4 significant figures. Okay, so it depends on your instrument how many significant figures you're going to report when measuring in the lab. Alright, if you can't answer the questions that we started at this tutorial, you need to go back to the end of the slide and I will see y'all in class.